Okay, so uh, so let's continue on to chapter 9. Uh, so so in chapter 9, we're going to be focusing on the trigonometric identities. So on the trig cheat sheet, so most of the relevant trigonometric identities we're going to use are located on the second page. Um, so in so in section 9.1, we're gonna focus on the first three sets here on the left column. So the tangent and cotangent identities, the reciprocal identities, and the Pythagorean identities, right? So section 9.1 is on this set here. Section 9.2, if I remember, is the sum and difference formulas. So that's this here. And then section 9.3 is the double and half angle formula. So the double angle formula is here. The half angle formula is here. And so probably we don't do the sum to product formulas. Okay, so and then 9.5 is on solving equations, but again, mostly using the identities here. Okay, so today we're going to focus on, again, these particular identities here. So in the first page of the section 9.1 worksheet, it's just basically explaining where these particular identities come from, right? So in as for the reciprocal identities, they're just basically coming from the formulas given by the unit circle, right? So you can see that if you compare sine and cosecant, right? So sine is y over 1, whereas cosecant is 1 over y. And so the two formulas themselves are just reciprocals of each other. And then similarly for cosine and secant, and then tangent versus cotangent, right? So in terms of their formulas, they're just reciprocals of each other. So so that's where the reciprocal identities come from. Right? So secant is the reciprocal of cosine, cosecant is the reciprocal of sine, and then cotangent is the reciprocal of cotangent. And additionally, you can see the relationship between sine, cosine, and tangent, right? So the formula for tangent is y over x, but y is just sine, and then x is just cosine, right? So that means that tangent has to be sine over cosine. So that's where that formula comes from. So basically, the tangent and cotangent identities and the reciprocal identities, right? So the two sets here, again, are just coming from the unit circle definition of the trig functions. And we use the unit circle definition here, but it's exactly the same for the right triangle, right? So if you compare the opposite, hypotenuse, and adjacent formulations for the trig functions, they have exactly the same relationship. Okay, so so that's where these identities come from. In terms of how they're used, typically when we're working with identities, most of the times we want to reduce everything in terms of sine and cosine, because those are the two main trig functions, right? So, so I mean, first of all, if you see cosecant, secant, and cotangent, typically you want to use these identities to write them in terms of sine, cosine, and tangent, and then tangent in terms can be again written in terms of sine and cosine, right? So the usage of these identities typically is to reduce everything to being written in terms of sine and cosine. Okay, so those are those basic trig identities. And one thing about notation is when we get to the Pythagorean identities, you can see that we starting to have powers of the trig functions, right? So here you have sine squared, but how you think of the powers, you want to be very careful about that, right? So when we write like sine squared like this, where the power is with the function, the way you should think of this is that the whole sine function is being squared, right? So what that means is like, say I give you an angle, like 30 degrees or something. The way you would calculate it is to first take the sine of 30 degrees, that happens to be 1/2, and then the result of that is being squared. So that's what this expression means. What it doesn't mean is that the power does not apply to the angle, right? So this is something completely different. Whereas the way you do this calculation is you square the angle first, whatever that turns out to be, and then you apply the sine function to that angle, right? So so these two things are different, and when you see when we write it like this, it actually means this particular way to write it instead of this. This is completely different, and then this is very rarely used, right? So most of the times when we have powers, this is what we mean.
Professor Val?
Yes.
Can you just write out an example real quick so that way I can make sure that what I'm thinking is the same thing that you're saying?
Yeah. So let's say okay. So I'm gonna work in radians, because again that's let me okay. So let me write it down here, so we have a little bit of space, right? So so like say I want to calculate sine squared of pi over 6. So what this means is, again, the power is being applied to the entire function like this, right? So I would write it out like sine pi over 6, and then this thing squared. So in terms of the order of operations, you always do the thing inside the parentheses first, right? So so what does this come out to be? Well, so you do sine of, make sure I'm in radian mode, right? So sine pi over 6. This is a special angle, right? So it's just going to come out to be 1/2. Right, so sine of pi over 6 is 1/2. And then the result of that is being squared. Right, so 1/2 squared would be 1/4. Okay, so that's that. Whereas if I write out sine pi over 6 squared like this, right? So again, you follow the order of operations where the pi over 6 is being squared first, and then the sine is being applied to the result of that, right? So this would mean sine of pi squared over 36, right? So this part is being squared first, and then and then now we do the calculation. It's a sine pi squared over 36, and if I calculate this, it's something completely different, right? So 0.2707. Okay, so these two things are not the same.
Thank you.
Yeah, so that's, and then so be careful about how you think of the powers of the trig functions, right? So they when we have powers of the trig functions, we typically almost always mean the first thing that I've written here, right? So this expression. So like, I mean, really, what does it mean to square something? It means that you multiply that thing by itself, right? So this thing would be sine of theta times sine of theta, whereas this thing means sine of theta times theta. Okay, so again, these two things are these two things are different.
Thank you, Professor Bell.
Okay, so so in terms of the Pythagorean identities, I mean, the reason it's called the Pythagorean identity is exactly because it comes from the Pythagorean theorem and right triangles, right? So if you draw in a right triangle with hypotenuse 1, right, and then the two sides are x and y, so that's exactly how you fit in a right triangle into the unit circle, right? So this kind of right triangle, and then if you write out the Pythagorean theorem, it's just y squared plus x squared is equal to 1, right? So this squared plus this squared is equal to the hypotenuse squared. But then y and x for the unit circle is just sine and cosine, right? So y squared is just sine squared, and then x squared is just cosine squared, and then again, when you write sine squared like this, the shorthand way to do it is to put the power with the sine part, right? So this is where this Pythagorean identity is coming from. So that's the first one. The first one here, right? So sine squared plus cosine squared is equal to 1. And then the other two Pythagorean identities are just coming from the main one, right? Because as I say, the sine and cosine are the two main trig functions. The other ones are just derived from sine and cosine, right? So if you take this equation and you divide everything by cosine squared, right? So this thing divided by cosine squared, this thing divided by cosine squared, and then this thing divided by cosine squared, then it produces this identity, right? Because sine over cosine is the same as tangent. Cosine over cosine just cancels out because you're dividing something by itself, right? So that's just 1. And then 1 over cosine is the same thing as secant. So that's where this formula comes from. And then if you do the same thing and you divide by sine squared, then you get the other Pythagorean identities. Right, so basically these two are just derived from the first one by the relationship between sine, cosine, and the other trig functions. Okay, so that's the Pythagorean identity, and what the Pythagorean identity essentially is saying is that no matter what angle theta you take, if you plug it into this formula, it will always calculate to be 1, right? So for example, I do sine squared of, so let's just choose some random angle, right? So it's like, say, 27 degrees plus cosine squared 27 degrees, right? So I mean, sine of 27 degrees is going to be like point something something, like 0.4 something maybe, right? And then cosine of 27 degrees is going to be point, I don't even know, like 0.7 something maybe, right? So it's some long decimal number, and then if you square sine and then you square cosine and then you add them together, they'll always be equal to 1, right? So we can check that, right? So here I've written it in degrees, right? So before I was working in radians, so let's make sure I'm working in degrees now, right? Degrees, right? So you see how sine of 27 degrees is some long decimal number. Cosine of 27 degrees also is some long decimal number, right? But now, if I do, so the first one squared plus the second one squared is a 0.439904997 squared plus
Professor,
0.8910065242 squared, right?
Professor,
So the sine squared plus the result of the sine squared plus the result of the cosine squared. It's not going to be exactly 1 because I'm approximating here, right? Because I'm using the decimal approximation. So you can see that, I mean, it should be equal to 1, but it's being approximated. So this is, it's just some number that's very close to 1.
Professor.
Yes.
Yeah. You can copy paste the answer calculate.
Yeah, I can. Yeah, I didn't have to type it out like that. No, that's not what I want. Okay, I mean, I didn't have to. I could just type the whole function in, right? So sine of 27 squared, right? So as I said, when you square the trig function, you should really think of it like this, right? So and then plus cosine. Oops, I need the extra parentheses. Cosine 27 close squared, right? So sine squared plus cosine squared. Now it's exactly equal to 1 because now I'm not approximating. And again, this is true no matter what angle you try to calculate this with. So that's what this identity is saying. Again, it's essentially coming from this right triangle with hypotenuse 1. Okay, so those are the Pythagorean identities. So any questions on the identities? Okay, so that's where these identity comes from. So the next thing we'll just discuss is the even odd formulas. So I mean, basically the even odd formulas just describe how the trig functions behave when the angle becomes negative. and there's two different behaviors. So the even behavior and then the odd behavior. So for the functions that are even, which cosine is an even function, what happens is that when you have a negative angle, it's same as if the angle, the function behaves the same as if the angle were positive. That's what this formula is saying. And then for an odd function, which sine has the odd behavior, when the angle is negative, basically the negative comes out of the function, and you get it like this. So what do we mean by this? So even and odd is referring to the symmetry of the function, right? So there, out of the 6 trig functions, cosine and secant are the 2 even functions, and the other 4 trig functions have the odd symmetry, right? So these are odd, and these are even, right? So you can see the kind of symmetry by looking at the shape of the graph, right? So here we have the shape of the cosine function, and the symmetry for this graph is if you cut the graph in half along the y-axis, then the left half and the right half are just mirror symmetries of each other, right? So you see, if I take this half of the function, I flip it around, it's exactly the same as the right half, right? So this is what we call reflection symmetry along the y-axis. And if a function has this kind of symmetry, it's called even. And you can see that secant also has the same thing, right? So if you cut the graph in half, right at the y-axis, then the left half and the right half are just mirror images of each other. So that's even symmetry. And then odd symmetry is a little bit harder to see. Odd symmetry is rotational symmetry, right? So if you mark off the origin, and then you take the right half and you rotate it 180 degrees, then you get the left half, right? So imagine taking this half. You say you take this hump in the sine function, and then I rotate it around, it'll turn upside down here, right? So odd symmetry is rotational symmetry around the origin. So you can see it for the sine function and then the other functions, right? So for tangent, if I take this piece here and I rotate it around the origin, it'll turn into this piece here. And then similarly, cosecant, if you take this piece here, you rotate it around, it turns upside down to this piece here. And then here, if you take this piece and you rotate it around, it looks like this piece. Okay, so this kind of rotational symmetry is odd. This kind of mirror symmetry is even. And that reflects, so the kind of symmetry reflects on how the function behaves in terms of negative angles, right? So you can see that if I calculate the cosine of negative 120, it's the same as calculating the cosine of positive 120 degrees, right? So these two turned out to be negative 1/2, right? So in terms of the unit circle, right? So in terms of the unit circle, right? So 120 degrees is here, and then negative 120 is actually the same thing as 240 degrees, right? Because that's the coterminal angle. And for the cosine function is the x-coordinate, right? So the x-coordinate here is exactly the same as the x-coordinate here, right? So that's basically what the even symmetry is trying to indicate, right? So you can see that the x-coordinate on the top half of the unit circle is always the same as the corresponding x-coordinate on the bottom half, right? So this is the same as this is the same as this is the same as this, and so on, right? For the x coordinates, right? Because basically, whether y is positive or negative, the x is the same when you're going up and down like this, right? So that's what it's being described for cosine here, and odd symmetry, right? So it says that if you calculate the sine of negative 45 degrees, it's the same as taking the positive angle, but then taking the negative of that value, right? So so basically, what this is saying, at least in terms of the unit circle, right? So sine is for the y coordinate, right? So what it's saying is that, again, you're comparing the top half to the bottom half, right? So it's essentially just saying that the y coordinate of the things on the top half are the opposite of the y coordinate of the things on the bottom half. As you can see, the y coordinate here is positive, the y coordinate here is negative. The y coordinate here is positive, the y coordinate here is negative, right? So that's what it's describing, at least in terms of the unit circle. Okay, so that's even in odd symmetry. So any questions on even and odd symmetry?
Nope.
Okay, so I mean, at least in terms of this course, we're not going to actually use the even and odd symmetry all that much. It's used a little bit in calculus when you talk about integration, because integration is referring to like areas under the curve, and when you have symmetry like this, you can see that the area here is exactly the same as the area here, and then the area here is exactly the same as the area here, right? And so if you exploit the symmetry of the graph, you can understand the area in an easier way. I mean, say similar here. The area here is the same as the area here, except this is right side up and this is upside down. Well, but in any case, we don't use it all that much in this class. So for the purpose of this section, the main identities we want to be familiar with is what the identities that are on the first page here. Okay, so what are we going to use these identities for? We're going to try to simplify complicated trig expressions into simpler things by applying the various identities. So you can see here, I've written down a few expressions that have multiple trig functions together. I mean, the ones on this page at least aren't too bad. It's just two trig functions written together. But in most cases, in a lot of cases, because everything can be related to sine and cosine, there's typically a much easier way to represent these expressions, and so we want to use the various identities to try to simplify things that are written in terms of trig functions like this. So when we're trying to simplify things using the trig identities, there's no general procedure that you always. So I mean, you're not always using the same identities every time. So to become familiar with these kinds of problems, it just takes a bunch of practice to try to build up intuition. But there are a few things you can keep in mind to try to figure out which is the correct identity to use, right? So again, first of all, the identities are on the second page of the trig cheat sheet, and then in particular, we're focusing on the three sets here, right? So the tangent and cotangent identities, the reciprocal identities, and the Pythagorean identities. So you apply any identities that are relevant, and then once you apply the identities, you use the algebraic methods to simplify, cancel, reduce as much as possible. I mean, so what do I mean by this? Right, so like if you have sine over sine, right, so something divided by itself, it cancels out, right? So you simplify it, and then if it's possible, where things cancel out, try to write everything in terms of a single trig function. Okay, so that's the idea here. So let's try to work out some of these problems. So one thing to keep in mind in deciding which identities to use, right? So again, this is not a general rule, so you shouldn't always follow this every single time. But I mean, if you look at the expressions on this page here, there aren't any powers, right? So I mean, here you just have like cosine and secant, and then here you have cotangent and so on. So if powers aren't involved, typically you want to use these here, right? So either the tangent or cotangent identities or the reciprocal identities. Whereas if you see things being raised to the second power, then maybe you want to use the Pythagorean identities, right? So I mean, there's no reason to use the Pythagorean identities if you don't see anything being squared, right? So that's one thing to keep in mind, right? So these don't have anything squared, so you don't want to use the Pythagorean identities. Whereas if you go to the next page, then you start seeing like secant squared here, and then cotangent squared here, right? So things are being squared here. So then maybe you want to introduce the Pythagorean identities. Okay. So that's one thing to keep in mind. And another thing to keep in mind is that, again, sine and cosine are the basic trig functions, right? So typically you want to use the identities that reduce everything in terms of sine and cosine. Right? So if you see tangent, you want to think of it as sine over cosine. If you see cotangent, you want to think of it as cosine over sine. And if you see cosecant, you want to think of it as 1 over sine. And if you see secant, you want to think of it as 1 over cosine. Right? So these four identities reduce everything in terms of sine and cosine. So with that in mind, right, so we see this first thing here, I have cosine and I have secant. Right, so secant, I can reduce it in terms of cosine by using this identity, right? So secant is just 1 over cosine. So that's the one I want to use. Right, so let me just make a note of here, right? So which identity am I using? I'm using that secant x is equal to 1 over cosine x. So this is the identity I'm using. Yeah, so another thing to keep in mind is that the angles in the formula sheet are represented by theta, whereas here I've now replaced the angle by x, but it doesn't matter. I mean, it's just a variable, right? And you can use any letter you want for the variable. So here I'm using x. On the formula sheet, it's using theta, but x and theta are the same, right? So don't get caught up in that the variable is different. It's still the same formula. Okay, so I'm using the reciprocal formula for secant, right? So secant is 1 over cosine. So I just plug it into here, right? So what is this equal to? So you have cosine x, and then secant is now replaced by this thing, 1 over cosine x. And so now, what is this? it's cosine divided by cosine. And what does it mean when something is divided by itself? It just cancels out, right? So, right, so this is just cosine x over cosine x, right? But that cancels out, so this is equal to 1. Okay. And then there's nothing simpler than the number 1, right? So basically, cosine x times secant x simplifies to just 1. Okay. So any questions on this first example? So this one is pretty straightforward. We're just using a single identity, and then that identity allows us to do the cancellation, and we get 1. Okay, so let's look at the next example. Right, so I have sine x, and I have, what are the trig functions I have? I have sine, and I have cotangent. Right, again, between the two of them, I want to think in terms of sine and cosine. Right, so how do I relate cotangent to sine and cosine? Well, I have this one now, right? So this identity, cotangent, is the same as cosine over sine. So again, let me write down the identity that I want to use. Right, so the one I'm using is that cotangent is the same as cosine over sine. So now I just plug it right in, right? So this is replacing this, the cotangent, right? So when I write it out, what does it look like? So sine x times, and then this thing is replaced by this, right? So cosine over sine. And then again, I see I have sine divided by sine. So something divided by itself cancels out. And what am I left with? Just cosine. And then now it's just a single trig function, so there's nothing you can really do with that, right? So okay, so now this is as simplified as it can get. So we're saying that sine times cotangent is the same thing as cosine. Okay, so any questions on example B? Okay, so continuing on to the other two examples, they essentially follow the same idea, right? So I'm using the proper identity that relates things in terms of sine and cosine, and then applying some kind of cancellation. Except in C and D, now we're dividing things, right? So we can have fractions inside of fractions, but you just have to remember that dividing by a fraction is the same thing as multiplying by a reciprocal, right? So what do we want to do in C? Well, I have sine, which is okay. I don't need to do anything with the sine, but then I also have tangent. So I want to use an identity for tangent, right? So how do I relate tangent? So tangent, oops, let me change to green. So tangent is again the same as sine over cosine. So here the variable is t, but again, the variable isn't that important, right? It's just representing the angle. Okay, so tangent is sine over cosine. Right, so this goes into the denominator here. Right, so let's write it out. So sine divided by sine over cosine. But then I have a fraction inside of a fraction, so what should I do by that? Right, so if you remember, dividing by a over b is the same thing as multiplying by the reciprocal. Right, so let's do that. So what do we have here? So the numerator is sine, and then this division changes to multiplication, and then I flip this upside down. Right, so this becomes cosine over sine now. And then what do we have? This sine cancels this sine. And then what's left over? Just cosine. So in actuality, problem C is exactly the same thing as problem B. It's just written in a different way. Okay, ultimately, you get this expression, which is exactly the same as this expression. Okay, so any questions so far?
Nope, I'm good.
Okay, so let's continue on D. Again, it's going to be very similar, right? So I just need to break this thing down. So we have cotangent and cosecant. So now both of these I should relate in terms of sine and cosine. So let's do that. So what do I want to use? So for cotangent, I want to use cotangent is cosine over sine. And then for cosecant, I want to use 1 over sine. Okay, so this goes in for cotangent, and this will go in for cosecant. Okay, so writing it out, what do I have? So the numerator becomes cosine of t over sine of t. And then this fraction becomes this fraction. And then the denominator becomes this thing. So 1 over sine of t. And then, again, I have a fraction divided by a fraction, but dividing by a fraction is the same thing as multiplying by the reciprocal. So what is this equal to? So the numerator stays the same. And then times the reciprocal of the denominator. So sine over 1. And then again, I have a sine on top and a sine on the bottom. So this cancels with this. And then all I'm left with is cosine. And I can't do anything with the cosine, so I just leave that alone. So in actuality, D is actually the same as B, C, and D are actually all essentially the same problem. They're just written in different ways, and you see, in the end, they all turn into cosine. Okay, so so any questions on these 4 examples? So the basic idea is so if you have tangent, cotangent, cosecant, or secant, you want to use these 4 identities to relate things in terms of sine and cosine. And then once you write everything out in terms of sine and cosine, see where the cancellations occur and try to simplify from there. Okay. So that's that's this kind of example. So let's continue on to the next page. So the examples on this page are a little bit more complicated, because I mean, before, the simplification basically comes from a single cancellation, but on these examples, it might not just be a single line cancellation. But in any case, let's see what we can do. So looking at example E, so what can we do? We have a tangent and we have a cotangent. So if you're not sure what to do, you can follow what we did in the previous page and then write things in terms of sine and cosine. And it's possible to do it for this example, right? So like you would use tangent, you would use this one, and then cotangent, you would use this one, and then everything will be in terms of sine and cosine. And it's possible to do it that way for this example. However, if you're writing things in terms of sine and cosine, things become a little bit more complicated, and it might not be so easy to simplify things from there. So to make things a little bit easier, we can try to look for some other identities we might possibly be able to use, right? So the 2 trig functions here are tangent and cotangent. So you can ask yourself, is there an identity that relates directly these 2 trig functions? And there is, right? Because cotangent is just the reciprocal of tangent. So we can use that identity instead. Okay, so let's use the fact that cotangent is 1 over tangent. Okay. So let's write it out. So what do we have? The numerator stays the same because it's already tangent. And now I can write the denominator in terms of tangent. Okay, so now I have 1 plus tangent over 1 plus 1 over tangent. So everything is in terms of tangent, and now I have to simplify this thing here. Okay, so what can I do? So I have a fraction inside a fraction, so I can look to find the common denominator. And the common denominator, there's only a single denominator, right? So tangent, so that has to be the common denominator. So I can cancel the denominators by multiplying the top and the bottom by tangent. Right, so I have to multiply both the top and the bottom by tangent, because to keep everything equivalent, whatever you do to the numerator, you also have to do to the denominator. Right, so I multiply the top by tangent. I multiply the bottom by tangent. Okay, and then I have 2 things in the numerator and 2 things in the denominator, right? So I need to distribute. So what do I get? So tangent times 1 is tangent. Tangent times tangent is tangent squared. Okay, because something times itself is just that thing squared. tangent times 1 is tangent. And then this is tangent over tangent, so that cancels out to just 1. Okay, so I have this thing. And now how can I continue from here? Well, in the numerator, I have a tangent in this term, and then I have tangent squared in this term. Okay, so since both terms contain tangent, I can factor out tangent. So what do I get? So basically there's a common factor here and here. All right, so I factor out the common factor. So if I factor out tangent, there's 1 left over here, and there's 1 more tangent left over here. And then, what is the denominator? Tangent plus 1. But 1 plus tangent and then tangent plus 1 are the same thing, right? Because when you're adding two things, it doesn't matter which order you add them in. So this is the same as this, right? So they just divide each other out. And what am I left over with? Just tangent. Okay, so now it's just a single trig function. And so I am done. I mean, you can write it as sine over cosine, but that's not completely necessary. Okay, so that's example E. So I mean, in the end, again, we only really need one identity where I can relate cotangent to tangent using the reciprocal identity, but then the process to simplify things becomes much more complicated. So you might have to use different algebraic tricks to try to figure out how to simplify it. Okay, so any questions on example E? Okay, so looking at F and G, I see I have the square of the trig functions, right? So this is where I want to look at the Pythagorean identities. Okay, so what Pythagorean identity do I have for secant squared? So what do I have for secant squared? I have this identity, right? So secant squared is equal to tangent squared plus 1. So secant squared x is equal to, again, tangent squared plus 1. So this goes in here, right? So what do I have? So tangent squared x plus 1 minus 1. Right, so this plus 1 and then this minus 1 over sine squared x. Oh, this should be in blue. Okay, so plus 1 and minus 1, that cancels out. So what am I left with? So tangent squared over sine squared. And then now I still have two trig functions, right? So tangent and sine. So how can I relate tangent and sine? Well, tangent is sine over cosine, right? But it's tangent squared, so you can just square everything, right? So tangent squared is sine squared over cosine squared. Okay, so now I'm using a second identity. So this will go into the numerator. So what do I have? Sine squared over cosine squared over sine squared. And again, dividing by something is the same thing as multiplying by the reciprocal. Right, so you have sine squared x over cosine squared x times, right, so reciprocal of this, right, so this is over 1, right, so reciprocal of this is 1 over sine squared. And what am I left with? 1 over cosine squared. Kind of running out of space here. Right, so 1 over cosine squared. But what is 1 over cosine squared? Well, 1 over cosine is the same thing as secant. So I'm actually using a third identity here, right? So 1 over cosine is using that 1 over cosine is the same thing as secant. Okay. So let me not confuse it with the other one. Okay, so that's example F. And so basically, I mean, you might have to just continue looking for different identities until you can't simplify the expression any further. But again, there's no real general procedure that tells you which identities you should always use and so on. Okay, so let's finish up the last two examples. So here I have cotangent and cosecant. Right, so cotangent and cosecant. But squared, right? So cotangent squared and cosecant squared. So there's this last identity. 1 plus cotangent squared is equal to cosecant squared. So let's use that. Right, so what am I using? So cosecant squared x is equal to cosecant squared is equal to 1 plus cotangent. Right, so this thing, this is going to go here. So let's write it out. So cotangent squared minus this thing, but this thing is replacing a single thing, so I need to put in parentheses here. Plus cotangent squared. And then now this distributes. So what do I have? Cotangent squared minus 1 minus cotangent squared. Then this thing minus itself, so that cancels out. So I'm just left with minus 1. Okay, so that one wasn't too bad. And then finally, the last one, which is probably the most complicated one. Okay, so this one is set up slightly differently, where they're giving you an equation and they're asking you to simplify the left-hand side so that it looks like the right-hand side. And the basic idea is to start from the left-hand side, which typically will be the more complicated thing. So I'm starting from the left-hand side and apply a series of either identities or simplifications, and then the final result should look like the right-hand side. Okay, so let's start off, right? So I have two different trig functions, tangent and sine, and then the final result only contains cosine. So my first thought should be to try to relate everything in terms of sine and cosine, and I can do that with for tangent, right? So what am I using? So I'm using that tangent is sine over cosine. Okay. So, but this is 1 over tangent, right? So that means that 1 over tangent is the reciprocal. So to save some space, I'm just gonna do this in once. So tangent is sine over cosine, but 1 over tangent is the reciprocal, right? So 1 over tangent is cosine over sine. Okay, so that's what I'm using here. Right, so this becomes cosine over sine. Right, so I'm making this substitution into here. Well, into this thing. Okay. So now I have two fractions with the same denominator. So I can just add them together. All right, so what does that become? Cosine plus 1 over sine. And then this whole thing squared. So I have this. And okay, so now where can I continue from here? Well, when you square a fraction, that means you're squaring both the top and the bottom. Right, so what do I have? So it's cosine of x plus 1 squared over sine squared of x. Yeah, so the square just goes on the top and the bottom. And okay, so now I have sine squared in the denominator, but again, the end result is only in terms of cosine. So how can I relate sine squared to cosine? Well, I have the Pythagorean identity. So sine squared is plus 1 is sine squared plus cosine squared is equal to 1. But so that's what I'm going to use. So sine squared x plus cosine squared x is equal to 1. But let's just write this in a slightly different form. So sine squared x is equal to 1 minus cosine squared x. So this is going into here. So what do I have? So cosine x plus 1 squared over 1 minus cosine squared x. So I'm almost there, right? So I have this and this. So now how do I simplify this to look like the final result? So in the denominator here, it might not look like it, but what do I have? I have a difference of squares. Right, so how should I think of this? Right, so say I have 1 minus a squared. So this is a difference of squares. How do I factor something like this? It factors as 1 plus a times 1 minus a, right? Where in this case a is cosine, right? So what does this become? So cosine of x plus 1 squared over, right? So I'm factoring it in this way. So 1 plus cosine x times 1 minus cosine x. A is just, cosine is playing the role of a here. And then finally, right, so again, cosine plus 1 is the same thing as 1 plus cosine because adding is commutative. Right, so I have one copy of this, and it cancels out one copy of this. And then now this thing is the same as the numerator here, and then the denominator here is the same as the denominator here. And so now I'm done. Okay, so this one was a little bit more complicated, but basically you just keep applying different identities and then seeing what kind of simplifications you can do until the final result looks like the thing that you want. Okay, so yeah, so again, there's no general procedure for these kinds of problems. So I mean, there might be some trial and error involved when you're practicing these kinds of problems.
Professor Bo,
yes.
could you please scroll back down to the bottom again? I didn't finish. Okay, yeah, I just wanted to make sure I got everything. Okay, thank you.
Yeah, so there's there's no general procedure for these kinds of problems. Just look for different identities that you can use that relates to the various trig functions that you're working with, and remember the various different algebraic tricks that might be involved. Right, so like how to deal with fractions, like dividing fractions, adding fractions, and so on. And then here we have a difference of squares, and so on. Yeah, but again, there's no general thing that says, okay, you should use this trick or you should use this trick. That basically just boils down to intuition that you build while practicing these kinds of problems. Okay, so any questions on this in this section? So again, section 9.1 focuses on these identities, right? So those are the ones that you're looking for.